Real life.
Good evening, everyone. Today we've gathered for the iFocus Online Optics and Refraction series, and we are here for lecture number 2 by Dr. Navneet Sidhu on wave optics, diffraction, interference, and polarization. Welcome to everyone. So, let me also introduce the moderator for today's session. We have Dr. Lakshay Dudeja, sir. He has done his MBBS from Maulana Azad Medical College, Delhi. He's done his MS Opthal from Kasturba Medical College, Mangalore, and also fellowship at Arvind, Salem, and Madurai. Sir specializes in anterior segment cornea and microsurgery. Sir has also done an ICU fellowship at Kellogg Eye Center, Michigan, and he's worked as a medical officer at Arvind Eye Hospital. Presently, Sir owns his own Dudeja Eye and ENT Care Center in Sonipat, and Sir had also been a part of CFS family. Welcome, Sir.
Thank you so much.
Let me also introduce the chairperson for today's session, Dr. Uma Sridhar, ma'am. She has done her MBBS, MS, and DNB, and also FRCS. And she has done her FRCS from Royal College of Surgeons, Edinburgh. She's done a fellowship at LV Prasad Eye Institute in cornea and anterior segment. She's a senior consultant in cornea anterior segment at Eye Care Eye Hospital and Postgraduate Institute, Noida. Ma'am is also a DNB coordinator and nodal officer. Ma'am has multiple surgeries like thousands of phaco, ECC, and PKs to her name. She has done multiple DSEC, DALC, FALC, PTK, PRK. And ma'am also mentors a lot of guide students and has contributed enormously to the publication online as well as in various presentations throughout the national and international conferences. We welcome ma'am. Ma'am will be joining in some time. Let me also introduce the speaker for today, Dr. Navneet Sidhu. Ma'am has done her MBBS from Government Medical College Hospital, Chandigarh, and MD Ophthalmology from the prestigious RP Center for Ophthalmic Sciences, AIMS, New Delhi. She's also done her DNB in 2020, and currently ma'am works as an associate consultant at Center for Sight, New Delhi, and she specializes in cataract, cornea, and refractive surgery. She also has multiple publications in various international and national journals, and she's a gold medalist in ophthalmology. So welcome, Dr. Navneet, and over to you for today's class.
So we have heard many lectures from Dr. Navneet, and she's a very good speaker, and I hope she'll do justice to this, and we are 100% sure that she will do it.
Thank
So
you,
ma'am,
sir.
you can start now. Yes.
So good evening, everyone. Today we'll be discussing diffraction, interference, and polarization aspects of wave optics. So basically, what is light? According to Newton's theory and Huygens' theory, they both had contradicting features about the light. So Newton described light as a particle, whereas Huygens described light as wave. So, of importance to us is Huygens' theory, since it was more reliable and apt. He described the wave nature of light. And both Newton and Huygens eventually performed an experiment in two rooms separated by a door. So, what was this experiment? So, he basically got this idea from a simple observation. So, two rooms were considered with an obstruction in the middle. So, we say that this is a wall with a door in between. So Newton considered this as a boundary and Huygens considered this as a door. So this was the obstacle between two rooms and light was switched on in one room. So according to Newton, if light was of particle nature, it would travel in straight line through this obstruction. And so the first room, which was fully bright, would cause some portions of the second room to be bright and the rest of the room should be dark. But what they observed was that the first room was bright as usual and the light spread in the second room as well uniformly, but it was not as bright as the first room. Therefore, Huygens' theory was proved through this simple experiment, and hence it was proposed that light was of wave nature. Few other experiments were performed. So Thomas Young in the year 1800 performed a double slit experiment and hence confirmed the wave nature of light. And Maxwell in 1860 proved that there is visible light in the electromagnetic spectrum and hence supported the wave nature of light and also predicted the speed of light. So again, there's a controversy whether light is a particle or a wave. So if light was of particle nature, we can explain a few effects which are caused by light, like photoelectric effect and Compton effects, which are used in our day-to-day machineries and various other optical instruments. And if we consider light to be of wave nature, then explains the concepts of interference, diffraction, and polarization, which we'll be discussing in the today's lecture. So wave, as we have read before, also has various characteristics. Amplitude of the wave. So amplitude of the wave is the maximum displacement from the equilibrium position. Say this is the equilibrium position, this black line, and maximum displacement of the wave from this equilibrium, whether in the upward direction or downward direction, is defined as amplitude. Then next is phase. So state of motion in which the wave sweeps through an element at a particular position. So say this is an element and this is a single wave which is going in a uniform direction. So this will be a in phase wave. And if we see two different waves, however, not in sync with each other, these are out of phase waves. And if the two waves are completely moving in different directions, these are completely out of phase waves. Then comes wavelength. So wavelength is the distance between two consecutive crests or troughs when in the same phase. So like this is a wave in the same phase. The highest point is called as a crest and the lowest point is called as a trough. So the distance between two consecutive crests or two consecutive troughs is called as wavelength. Time period. So time period is one complete oscillation. So again, time taken from one crest to the other crest or from one trough to the other trough will be called as time period. And frequency will be the number of oscillations per unit time. For example, per second, per minute. So that will be the number of oscillations happening, which will be defined as frequency. Then coming to wavefront. So wavefront is like, we know that whenever light travels, it will not travel in a single line. It will have multiple waves. So locus of all the points having same phase at a given point of time. So like these are multiple waves traveling in one direction. So the crests or the troughs, when multiple waves form to collect together and they are in the same phase, this will form a wavefront and they are moving in the same direction. So the shape of a wavefront will depend on the source of disturbance. So it will be always normal to the light rays and it will never propagate in the backward direction. It will always move forwards. So we'll be discussing about this later on. So wavefront can be either spherical, cylindrical or plane. So these are the three different shapes that a wavefront can form. So spherical wavefront is the most commonly seen and most commonly used in optical instruments. In this, there's a point source of light, which is dimensionless. It's a single point source of light. It releases concentric rings of light. So its application is used in wavefront aberrometry. So wavefront aberrometry basically is used to measure and analyze the aberrations of the optical system. So we can analyze both lower as well as higher order aberrations via this instrument. So there are different types of aberrometers. We can have outgoing wavefront aberrometers, ingoing retinal imaging aberrometers, and ingoing feedback aberrometers, all of which will be discussed in detail in the upcoming classes. So this is a picture of various aberrations which we can measure using aberrometer. So we can measure spherical, cylindrical, or tilt, comas, or higher order astigmatism. Then next is plane wavefront. So in plane wavefront, when a small part of a spherical or a cylindrical wavefront, it originates from a distant source, say infinity. So this will form a parallel beam of light. So these will be in the same plane in a single direction, but like a square or a plane. So this concept is used in a wavefront guided LASIK surgery. Then next is cylindrical wavefront. So in this, we have a slit source of light so that all the points are equidistant from the source. So when these rays of light pass through a lens or a converging lens, they will converge at a single point source. So basically in a cylindrical wavefront, they originate as straight lines, but they will converge at a single point. So again, this concept is used in wavefront guided LASIK. So this is the gross image of all the three types: spherical aberration, wavefront originating from a point source; cylindrical wavefront originating from plane source but converging to a single point; and plane wavefront with light originating from infinity. Now, let's discuss about interference. So interference is basically superposition of two waves to form a resultant wave of either greater, lower, or the same amplitude. Now, interference, how will this happen? Either it can be constructive interference, wherein two waves are coming in, joining together, and will form a resultant wave of greater amplitude, or it can be a destructive interference, wherein the waves will form a resultant wave of lower amplitude. So difference between both constructive and destructive interference is very easy, very simple to understand. In a constructive interference, the crest of a wave will overlap with the crest of another wave. Hence, this will add on to the amplitude. So resultant amplitude will be sum of both the individual waves' amplitude. Hence, will form a wave which will have a resultant amplitude which will be higher as compared to that of individual waves. Hence, the name constructive. Whereas in destructive interference, crest of one wave will meet the trough of another wave. So hence, the resultant amplitude will be the difference of amplitude of the two individual waves. So the resultant wave amplitude will be less as compared to those of individual waves. So to explain this phenomena, Young he did a double slit experiment to prove both the wave nature of light and also to explain the phenomenon of interference. So interference will only take place when coherent sources of light are present. So coherent sources of light means when more than one light source are in the same phase, are of same amplitude. So he did this experiment in two setups. So in setup 1, an ordinary light bulb single source was used, so which we can label as a coherent light source. Light was made to pass through a thin slit, which was comparable to the wavelength of light. So it was a very thin slit. This light was further made to pass through two different small slits separated by a negligible distance. And the final result was that alternate dark and light bands were seen on the screen. Further, he made a setup 2 in which two different light bulbs, which means that they were two non-coherent light sources were taken. They were made to pass through the same setup, a thin slit first and then through two small slits. However, in the second setup, no alternate bands of light were seen. So why alternate sources of light bands were seen in the first setup? So when the ordinary light source was made to pass through a small slit, the wavefront of the semicircle will be formed. So it is because there are obstacles present on both the sides. There's a obstruction with the small slit. So when the light hits that small slit, it will form semicircle shape. So this will form, these semicircles will further pass through two slits, and when the light waves, they cancel out each other, they will form alternate light and dark bands. So there will be points where red and yellow will also overlap with each other. So these areas of overlap will form a destructive interference, whereas same color, yellow bands and red bands will form a constructive interference. So because of constructive and destructive interference happening in the same setup, there are alternate dark and light bands seen on the screen. So eventually he concluded that when the light wave is originating from two coherent sources, they will overlap with each other both constructively as well as destructively at the same time. So this forms alternate light and dark bands of equal width. So this phenomena was labeled as interference. So it is hence proof that interference is a property related to the wave nature of light. So important results drawn from the above experiments are that bands, they were formed as a result of interference, and interference was due to the overlapping of wave nature of light. If light was of particle nature, the overlapping would have never happened. Then this pattern that we obtain, the alternating dark and light patterns, are called fringe pattern. So Bright bands are formed due to constructive interference. So they are the positions of maximum intensity. And dark bands are formed due to destructive interference, which are the positions of minimum intensity. So in constructive interference, the fringe width will remain the same throughout, which is called as a linear fringe width. So the intensity of fringes will increase if point sources are replaced with slits. And if there are slits instead of point source, more light will be able to pass through the slits, which will cause stronger wave fronts, and hence greater intensity fringes will be formed. So then interference was further explained to be of sustained nature. So positions of maxima and minima, constructive and destructive interference of light intensity will remain fixed throughout the screen and throughout the pattern. So this is hence called as permanent interference, since the intensity will not change. However, for this to happen, the light sources should be coherent, of same nature, in the same wavelength and same amplitude. And the point sources of light, they should be positioned very close to each other, and amplitude should be equal. So where do we use interference in our day-to-day practice in ophthalmology? So macular function tests, most common and most important of which is the laser interferometry. It uses these fringe pattern, and hence when the patient is able to infer the fringes clearly, we confer that the patient has a healthy macula. It is also used in tear film analysis, in LipiView, and in ocular surface analysis. It is also used to determine the quality of ophthalmic lens surfaces, which form alternate fringe patterns, which are called as Newton's rings. Also used in optical coherence tomography, both anterior as well as posterior, and in biometry to measure the axial length and other parameters inside the eye, which helps in determining the IOL master. Then coming on to diffraction. So diffraction is somewhat similar to interference. However, diffraction is a phenomena in which the light rays bends while passing through a slit or an opening, as compared to interference in which they were passing straight. So extent of bending of light will depend on the slit diameters, and it also causes alternate dark and light bands. However, it will vary in intensity. So then Young conducted a single slit experiment to prove this, which was our setup 2. So the two slits were replaced by a single slit in this case. After the light waves passed through the slit, a central bright band was formed, which was of maximum width and maximum intensity, followed by alternate dark and light bands, but with decreasing intensity and decreasing width on both sides. So this change in pattern was explained by the phenomena of diffraction. So what was happening is the central light rays were passing straight through the slit, hence intensity was maximum. However, the light rays at the edges of the slits, they were bending in one particular direction, and hence the intensity and amplitude of the light rays were decreasing. So when we compare both interference and diffraction, they both obey the principle of conservation of energy. That is, the energy is neither gained nor lost. It's just distributed. So in interference, it is distributed equally, whereas in diffraction, it is distributed in variable parts. So total energy overall is conserved. So as we can see in this graph also, when light passes, interference is when the light is of equal intensity, and diffraction is when the intensity decreases over time. So to differentiate between the two, interference is superposition of two waves originating from the narrow slits, whereas diffraction is superimposition of a continuous family of waves originating from point source on a single slit. So interference has narrow slit, however, diffraction has a single larger slit. Interference will form a equally spaced bright and dark fringe pattern, whereas diffraction will have a central bright maximum, which is twice as wide as the other maxima. And in interference, 2 point sources are present, placed close to each other, which cannot be split into smaller sources. However, in diffraction, only one source of light is present, which can be split into n number of sources when it passes through that slit. So where do we use diffraction in our daily ophthalmology? Again, its principle is used in optical coherence tomography. Also, most importantly, it's used in the manufacturing of multifocal IOLs. As we know, multifocal IOLs has multiple wedges and crests. So when light passes through those crests, it will give us various zones, and hence vision will be clear in all the distances. It's also used in X-ray diffraction, which is called XRD. So this principle is used in orbital X-rays to visualize the bony structures better. So it enhances the bony structures, and it is also used in fluorescein angiography. All of these will be discussed in details in the upcoming lectures. Now coming on to resolving power of optical instruments, how interference and diffraction will help us in determining the resolving power of optical instruments. So resolving power is basically inverse of the distance between two objects, which can be clearly seen as separate when viewed through the optical instrument. So better resolving power will form clearer image. So for example, we have 2 point sources, two lines. So resolving power is the distance between two objects which can be clearly seen through that optical instrument, be it a telescope, be it a microscope. So resolution is to distinct two different objects, and magnification is to enlarge two different objects. So these are completely opposite terms. So when magnification increases, obviously the resolution will decrease. It will be hard for us to differentiate, to distinguish between two different points. So how diffraction helps in resolving power of the telescope? So telescope has one objective lens and one eyepiece. So objective lens, when the light rays pass through it, creates an inverted and minified image at the first focal length of the eyepiece. So this eyepiece will resolve the images as distinct. And further, the eyepiece also magnifies the image. So when a ray of light passes through the objective lens, it should focus as a particular point, and that particular point should be the first focal length of the eyepiece. But because of diffraction, the image will get focused in and around a specific point. It won't be as clear. So if the diameter of the objective lens is large, more light will pass through it, and hence it will give a more detailed image. So we can understand this with a simple diagram. So objective, when we have an objective of a larger diameter, when the light rays first pass through it, it will get focused at the focal length of the eyepiece. And then when that minified and inverted image further passes through the eyepiece, it will form an enlarged and a clearer image. It will be inverted and diminished. So it will have a central maxima and a peripheral faint image, which is usually not seen by the naked eye. Then diffraction and resolving power of a microscope. So again, resolving power helps to magnify the image. Resolution helps to distinguish between 2 points closely placed with each other. So when the distance between 2 points is comparable to the wavelength of light, diffraction will occur. So again, explaining that resolving power will decrease as the distance increases. So magnification and resolution are completely opposite to each other. So like in a microscope, we have objective lens and we have two eyepieces. So when light passes through the objective, it gets focused at the focal length of the eyepiece, forms a minified inverted image. And hence, when this object further passes through the eyepiece, it forms a magnified inverted image at a distance. So why microscopes have two eyepiece? That is for to increase the depth perception so that both the eyes, they see the same image at the same time. Then lastly, talking about polarization. So polarization is basically the process of transforming unpolarized light into polarized light. So this concept is used in 3D movies, sunglasses, and polarized cameras. So what is a polarized wave? In a polarized wave, the vibration of the wave is confined to one specific plane. So it will be either in one single x axis, a single y axis, or a single z axis, but will be always confined to a specific single plane. And the vibrations of the waves will take place in one wave and is perpendicular to the direction of propagation. An unpolarized wave is one in which planar vibration changes randomly in short intervals of time. So the vibrations of one single wave will take place in multiple planes and is again perpendicular to the direction of propagation. However, they are out of phase waves. No two waves will be in the same phase at the same time. So, how to convert a unpolarized wave to a polarized wave? We can do it via polarites, scattering, reflection, or refraction. So, polarization can be either done in transverse waves or longitudinal waves. However, in transverse waves, polarization is observed much more easily since particles oscillate in different ways. So, it's easier to get them into the same phase. However, in longitudinal waves, the particles will oscillate only in one direction. So it is difficult for the light waves to convert from unpolarized to polarized. So how polarization can be done using Polaroid films? So Polaroids are basically thin sheets which have long chains of molecules aligned in one direction. So every Polaroid sheet has a pass axis, which is called as the gate of Polaroid through which light passes. So every Polaroid sheet will have horizontal and vertical pass axis. So whatever be the direction of Polaroid, the intensity of light which comes out will be always the same. So hence this concept is used in Polaroid cameras, wherein light from different directions will enter into the camera. The camera will focus through its lens those light rays onto the Polaroid film. Since Polaroid has a pass axis, both horizontal and vertical, when the light rays pass through it, it will be directly projected onto the film. Also, the concept of Polaroid is used in sunglasses, in which the unpolarized sunlight becomes polarized when it passes through these screens, and hence the intensity of light is greatly reduced. So, it prevents glare and brightness of the light also reduces. Again, it's used in Polaroid cameras, in window pane films to dim out the outside light, and in 3D glasses, wherein two polarized films they are positioned in front of each eye, and these change the images into different directions and hence gives a depth perception or a 3D perception. So one eye will have the film in say vertical gate pass, and the other will have the film in a horizontal gate pass. So aligning both the waves onto the retina will form a depth perception, will give a depth perception. So differentiating again, unpolarized will be in which vibrations will take place in any possible random plane. Polarized will be when vibrations take place in one single specific plane. And partially polarized lights are those in which it will have some polarized and some unpolarized components. So light will sometimes vibrate in a vertical plane, but sometimes in a horizontal plane. So how can we achieve polarization by reflection and refraction? So when an unpolarized beam of light falls onto a surface, the reflected and refractive waves seen are partially polarized. So the incident wave, say sunlight, is which is incoming is unpolarized light rays. So when the sunlight is reflected from a surface, the light waves will be parallel to the plane, following the various laws of light waves that we have already read. So the reflected light waves will be parallel to the plane and are polarized. However, a few waves will also be refracted depending on the refractive incidence and angle of refraction. So the refracted waves will be unpolarized with a few polarized components which will be reflected back. So this theory is explained by Brewster's law, which states that at any particular angle of incidence, reflected ray is completely polarized and the angle between reflected and refracted ray is 90 degrees. So this is the reflected ray and this is the refracted ray, and angle is usually 90 degrees between the two. So coming to the conclusion of this, wave nature certainly explains the concepts of interference, diffraction, and polarization. And why these are essential? These are essential in understanding the behavior of light and in understanding the various applications which we use in day-to-day optical technologies. Thank you.
Sorry, I completely forgot about the class today, and I think I missed.
It's okay, ma'am. As usual, Dr. Navneet did a wonderful presentation.
Thank you, sir.
Yes, very tough, actually, very tough to imbibe so much physics going on, and we have lost touch.
Yes, sir.
So, yeah, polarized glasses, I would like to ask. You said the light when it falls on sunglasses or something, so it has a gate axis and only one axis light will pass through. So what happens to the rest of the light?
The rest of the light will be refracted back.
Reflected?
Reflected back. It gets reflected back.
Okay.
So hence,
So my question is, if we have a normal film on the sunglass, which will just decrease the intensity, and as compared to a polarized film, which will also decrease the intensity because most of the light will be reflected back and only one axis light will be passing through. So how these two are different?
so sir, by sunlight, we are also talking about the ultraviolet radiations that come along with that. So
Mhm,
ultraviolet radiations, they have a different wavelength as compared to that of the visible light spectrum. So
mhm.
when they pass through a normal film, light film, all of the sun light rays and all of the ultraviolet rays will be absorbed by that film, although intensity will be decreased. Some of it will be reflected back, but the ultraviolet rays, being of higher wavelength, they won't get reflected as much. So they will surely enter through the film and hence into the eye. However, the polarized film, since sunlight has unpolarized waves, and unpolarized waves, like I discussed, some of it will be refracted, some of it will be converted into polarized light. So that ultraviolet rays or most of them are converted into polarized light rays. So they, being polarized, will get filtered out and hence will protect the eyes from both the brightness of the light and the ultraviolet radiation of the sunlight.
So you
After
mean to say
that,
polarization also helps preventing UV lights?
yes, sir. Hence, sunglasses are also called as polarized glasses.
Yeah. So as compared to a normal sunglass, a polarized glass will filter out UV lights as well.
Yes, sir.
Normal sunglass will not.
Will not. It's just a film. It's just a black film,
It
which
will
is
just decrease the frequency or
the intensity
intensity.
of light.
So polarized because it is reflecting back the rest of the light. Okay. Okay, I need to see it again. Okay, got it. So one more thing, Dr. Navneet, you talked about diffraction in multifocal IOLs, right?
Yes, sir.
So I would like to you to enlighten more on that. How multifocal IOLs diffraction is helping in that? Yeah.
So basically, multifocal IOLs are composed of various crests and troughs. We
Mhm.
have depressions and we have elevations on that lens. So when light rays, they are coming into the eye, they are coming from varying distances: infinity, intermediate distance, near distance. So depending on the aperture of the pupil, when we accommodate, when we look at a near object, we accommodate. The pupil tends to become smaller. However, in a pseudophakic eye, this accommodation is lost. So when we are looking at an object of near interest, the light rays will come from a near object and they will not come in parallel waves. They will come in a converging manner. When they fall upon that lens, when they hit these crests and troughs on the surface of the IOL, depending on the basis of this phenomena of diffraction, instead of passing straight through those crests and troughs, which we can consider as small slits, they will bend in different directions. So when light is coming from a near object, the bending will be much more acute. So that will make a clearer image onto the retina compared to an object, say, coming from infinity. So light rays from the center of that object will come in a straight manner. They will pass directly through the center of the lens and fall onto the retina, hence giving a clearer image. And now discussing about intermediate distance objects. Intermediate distance objects will have both straight waves as well as converging waves. So the straight waves will again pass through the center. However, the converging waves from that intermediate object will have a distance, will have a focal length of, say, higher as compared to that of a near object, and hence the angle of diffraction will be more obtuse. And so a clear image will be formed onto the retina. And so these multifocal IOLs give us a wide range of distances, a wide range of image formations without the need of spectacles to focus those light rays onto the retina.
Okay, okay. So it is the central addition of power plus the diffraction which
Yes.
helps focusing the near object, right?
Yes.
So it's the addition of power also in the center, and plus the diffraction, which will enable us give the different power. Okay, okay. So interference and diffraction. Diffraction, do you feel it is like an edge effect?
Diffraction does cause the phenomena of edge effect in monocular lenses.
Mhm.
Again, it's the same principle that at the edge of the lens,
It will
then
bend.
it will bend and
Yes,
give
yes.
that false image or ghost image.
Okay, okay. So Dr. Kanika, any doubts are there in chat box?
No, sir, no questions as of now.
Okay, very nicely presented. I think you covered many practical aspects. You discussed one phenomena and very nicely at the same time you told the clinical applications as well. Wavefront, they are used in abrometer, LASIK, interference, OCT, laser interferometry, LipiView, IOL master. So diffraction in OCT, multifocal IOLs, fluorescein angiography, polarization in sunglasses, 3D glasses. So very nicely done. One
Thank
phenomena and the clinical applications. And as you said, I think in detail, we everybody in everybody's interest in further lectures, in detail they will understand each and every instrument or any machine and how these phenomenon are used. So Dr. Uma ma'am, do you
Tell
have
me.
any comments, ma'am?
I'm so sorry. I entirely
Ma'am,
slipped
that's
my
okay,
mind
ma'am.
that it was today. No, no,
That's
I
okay,
think,
ma'am.
Lakshya, you said that she covered everything. Did she also cover specular reflection by, the Snellen's law that angle of incidence is equal to the angle of reflection, and then the
Yes,
rest
ma'am.
of the
Yes,
light is refracted? She covered that too, the specular
yes,
reflection, like in specular
yes, ma'am.
microscopy. So she
Yes,
did
ma'am.
that too. All right. And she has also, like you said, multifocal. Refractive and diffractive, did we have the difference between the two? And the
Ma'am,
diffractive, I mean, I don't know, not that I am very knowledgeable on those matters. I think she must have covered all that too, right? The
uh,
differences in the different multifocals,
ma'am,
whether
you can
maybe,
enlighten us, ma'am, if you want to,
no, no,
ma'am,
I
please.
want to know also. It's not because you want to
Refractive,
enlighten me.
diffractive.
I
I
would
didn't
Okay.
like
go
to be
into the
enlightened also. Yeah.
Yeah.
basically I didn't go into the depth of these because these
That's
will be
okay. I think they'll be
ultimately discussed.
covered in the future classes,
Yes,
right?
ma'am. Yes,
Yeah,
ma'am.
we
Yes, ma'am.
just covered the more difficult aspects of the physics part. So that's why
Yes,
there are no
ma'am.
questions in the chat box.
Yes, ma'am.
It's not, everybody's either absorbed everything or nothing. So that's one thing. Yeah. These are all in the class 11 and 12 physics that we used to learn before getting into MBBS, right? But it has a lot of application in our
Daily.
day-to-day life, and ophthalmology, I feel, is half physics.
Yes,
That's
ma'am.
why
Yes.
people like Holiday and these people, Barrett and all, some of them were engineers before they became medical people. So, a combination of engineer and medical people, there's a lot of, that's why they are able to come out with formulas and, instrumentation and all those things.
Yes, ma'am.
So I think ophthalmology is half engineering also.
Yes,
We have
ma'am.
to understand our machines as much as we have to understand our techniques of surgery,
Yes,
right?
ma'am.
So that's why these principles are extremely important. And even though I missed it, I can make out from what Lakshya said that you have done a wonderful job. So hopefully all this is online and I can go back and look at it.
Yes, ma'am.
Yeah, thank you.
Navneet,
So
I would
thank.
like to request one thing. You mentioned all the diagnostics and all the ways that we use the wave optics in day-to-day ophthalmology practice. It would be really very nice if you could just concise everything, and based on each part of the eye, if you could just give a gist of what all investigations are based on what from anterior to posterior, if
Okay.
that's okay. For
Okay.
all the students who
So,
joined recently.
okay. So basically, distributing the optical structure of the eye into various segments. It starts from the tear film, then moves on to the cornea, the aqueous humor, lens, vitreous humor, and finally, all these light rays are projected onto the retina. So these structures act as different surfaces on which the light rays will act differently. So here comes the principles of interference and diffraction on each level. So starting from the tear film, like I discussed, that it is the principles are used in lip review and ocular surface analysis. So thinking of the tear film as individual water droplets or say small lenses, individual lenses, when the light rays which are projected on to the tear film falls is sensed by the machine. So the light rays will diffract, that is, will bend in different directions, passing through each lens, and will also cause interference, will pass in the same direction or in the same phase through these droplets. So these images, which are reflected eventually from the retina onto the sensor of the machine, are interpreted and hence give us an overview of the lipid view or the ocular surface analysis. Then cornea, we use abrometers, which acts on the corneal level and on the lenticular level. So again, considering cornea and dividing it into different small points, and as well as the anterior and the posterior surface of the lens into various small points, when these light rays will pass through these structures and are the retinal image formed by this light is reflected onto the sensor of the machine, it will form various small images like those rings as seen in spherical abrasions I discussed. And any distortion on the reflected image will help us in determining where the abrasions lie at. So, for example, these abrometers, they give us a corneal image, a lenticular image, and a combined image of both the cornea and the lens, which is seen by the eye as a whole. So, through that reflected image, we can determine whether the abrasions are at the level of the cornea, whether cornea needs to be treated, or whether we need to treat the lens so as to give a clearer or a clarity in the image to the patient. Then I also discussed about macular function tests, in which I talked about the fringe pattern in interference. So basically, again, we send in fringes of light which are projected onto the retina, and we ask the patient how he's interpreting those fringes. If the fringes are interpreted as of equal alternating light and dark bands of the same width and in a straight line, it would mean that the macula is healthy, like the healthy rays of light are being projected or reflected back from the photoreceptors. However, if there's any distortion in the fringe pattern that the patient determines, say a central wider pattern or a curved line or broken fringes, then that would mean that some of the photoreceptors in the macula or some or maybe all of the photoreceptors are not functioning. And hence, depending on the fringe pattern that is determined by the patient, we can determine or analyze whether the macula is healthy or not. And the same principle is used in laser interferometry, which gives us a broad idea of what is the visual potential in a patient's eye when there's a media opacity, say a leukomatous corneal opacity or say opaque lens. And then I also talked about retinal imagings, which were OCTs. So OCT again follows this concept of diffraction and interference, wherein the image, the light reflected from the surface, various intervening surface on the layer of the retina, photoreceptors, your inner nuclear layer, ganglion cells, and everything, those reflect those light waves individually, and that is then sensed by the machine, and hence we determine whether so and so structure in the retina is healthy or not. And same concept is applied onto the anterior surface also, the cornea and the lens in OCT, in which we can see whether the collagen fibers are clear, whether the cornea is healthy. In cases of edema, the collagen fibers will uh, reflect light in various haywire directions, and hence we see those dark bands in edematous cornea. So that is how these principles are utilized in our ophthalmic instruments.
Very beautifully explained, Dr. Navneet, and I'm sure students have a lot to learn. It's not just a dry subject as most consider. It has a lot of applied applications in our day-to-day clinics and diagnostics. So, very beautifully done, Dr. Navneet, and explained in detail. Dr. Lakshay, sir, over to you now.
Yeah, if no doubts are there, we can call it a day.
Yes, sir. There are no questions as of now.
Okay, okay.
Thank you, Uma ma'am. Thank you, Lakshay sir, and thank you, Dr. Navneet, for a great
Thank
session
you.
today.
Thank you, ma'am. Thank you, sir. Thank you, Dr. Kanika.
Okay.
Thank you.
My apologies once again. Sorry. All right. Bye. Right.
No problem, ma'am. No problem. Thank you.
Thank you.